Exactly. Exactly and exactly. Okay. So we decided to write down whatever we studied so far about DCG, about ranking, and add them to the overlay file so that other people can have access to it. So where can I add them? That's a good thing. Oh, we have it here. User behavior model for vertical list view. N users for N in N. User N choices of an item. And its relevance are N. Why is R N like this? Mm-hmm. Okay. So here we are talking about threshold. E pi I. We can look at it as a reward as well, the boost or the, again, I did not. So let me give it to ChatGPT and see, improve the flow or something. Well, I don't wanna make this assumption that B should be a decreasing function. Mm, and we'll select item I if combined relevance and ranking effect exceeds a threshold eta. Mathematically, this is expressed as this. Users view items sequentially from the top of the list. They only consider items that satisfy this condition while ignoring. Okay, this is one assumption I have. Hence, for any item J ranked above item I, we have words the user bypasses all items ranked above I that fall below the threshold. They select item Y. That's actually a simple, good model, and I want to talk about it and see. They stop and do not consider any item ranked below. That's really good. Give me yeah. For each user and their choice of an item I depends on two factors: the item relevance, or NI, and a boost effect from the item's ranking position. The boost function is a decreasing function of pi. This part I wanna remove. Why should we have extra assumptions? If the combined relevance and ranking effect exceeds a high threshold eta, mathematically this is expressed as this. Since user view items sequentially from the top of the list, they only consider items that satisfy this condition while ignoring items that do not meet the threshold. Hence, for any item J ranked above item I, we have this. So Then I want to assume for the selected item our n of I is 1. Uh, do you see the difference, by the way? Um, when we have the threshold effect, we are saying order doesn't matter. Previously, when we said, okay, our item I was clicked, any item above item I had a less, or actually, even there we should not have decided that there is an order, like a decreasing order in the product of Rn j b pi j. Yeah, we couldn't say that. So that's actually, but we did it, which is wrong. Okay, let's go. Let's tell my story. I want to tell it like this. For item I, for selected item I, so we also have like time rounds of computing this stuff. So exactly, we assume that we know the bees. All right, let me. So let's go tell the story. Our n of I is 1, and at the first round, we set this to 1 over log 2 log 2 1 plus pi I. We assume R9 and well, if we assume B, it's fine. We don't need to assume Rn of I is 1. It will be eta over B0, sorry, BT, forget, BT of pi I. And because BT is less or more, BT is less, so eta over BT will be bigger. Pi I Rn of J I should have we don't know if B stays decreasing. Well, here, if B is decreasing, we are good because the other BJs will be less. So then we want to create the aggregate R. So we assume we have the B, we compute R's, we compute the aggregate R, which is the sigma. Now based on the computed aggregate, we defined the new B. How do we do that? Well, that's true. have this formula here. I don't know. So we have some of the R's defined, some of the R's are not defined for each consumer because we don't know their behavior for the R's after, right? So we say we don't define them. Then if I want to define the aggregate, I will define the R of that cell as the average over all of the R's over all the consumers that already passed through that item. So we define the R for them. Makes sense. And then for aggregate of J, what is J? Well, I already defined Rn of J plus for the ones that Rn of I is not defined, but if Rn of I is not defined, Rn of J won't be defined too. How is that possible? Yeah, we have this formula which is right, which says Rn of I is defined, which is 1, then Rn of J will be the ratio of the boosts Rn of I. Agreed. It is the formula here too. And then you're saying R aggregate of J. J is just not clicked on, so we already defined all of them. Yeah. So I think we can have very good. Now we define R aggregate T of position I as what will we define it as? Fraction, what is it, sigma over n r n of I defined over the same thing, just 1. Oh, sorry. Over n, no, over Now that we have the R aggregate, we can compute B's. Okay. Exactly. Recursive process with ranking and boost effect. Minor confusion in the final based on what you are proposing. Need aggregated relevance score at time step t, but the formula given seems to have the same term in both numerator and no. Calculate the intended. That's true. Exactly. Aggregate relevance score at time t. I across is defined. Yeah, that's it. True. In this. Give me the now we have the RNs. How can we find the B's? Just eta over B. Exactly, right? But which? Actually, we can say eta over B. But some of these are less than eta and some of them are above eta. And that's what I don't like about it. That's the whole thing I don't like about BCG is that DCG, sorry. DCG is that it's not based on a user behavior model. Okay, we are defining what user behavior model is. Alright, I like to write it down. I feel even if it's not complete, it gives a good conversation for us. So I don't want to say user behavior model. Yeah, the better title is how to separate effect of boosting from relevance. So this is a user behavior model, by the way, too. This is not DCG or BCG or whatever. So just for the initial state, we are using the DCG coefficients. Generating boost away from the item's relevance based on consumers' behavior, click behavior on a ranked list. Now we wanna what is the boost effect, right? We have a bunch of R defined for an item. One thing we can say is from all those click behaviors, we can say they are eta over bt of pi j, and we take the okay, that doesn't change. Okay, now we say it is the mean of them. Alright, that's a good idea. I like to try that and see how it goes. So we computed the aggregate, right? We computed the aggregate. Now for item I, we have users n in, for example, an sub of n. It was observed, and observed equals defined, and then we say, so we have RT aggregate of item I, and we know that Rn of I used to be BT, eta over BT of pi I, and then I can define BT of pi I as eta over Rn of I, and then I want to define BT plus 1 of pi I but that's stupid actually. It's over R aggregate T of pi I so at least we need two etas. I want to do it like that. This way, otherwise, if we go for the second round, uh, if an item is clicked, Rn of I will be the R aggregate. So that will T, and we don't progress. So this cannot be this, because this is just a one round and it closes. But if I say there is an eta 1 and eta 2, once something is clicked on, it is greater than eta 1. And what if we just say it is maximizing RT, RI, B pi I? It is the maximum. And actually include the effect of not being observed in the boost function. Which makes sense in a sense. You are very low, you are not seen. It is also an effect of ranking. This one doesn't work only if I make it eta 1 item. Or I can choose this behavior, argmax of this. And because if you remember, we also mentioned epsilon here. Because we're saying it is less than eta, but how much less than eta? And we also talked about Munzer's question that if, to be honest, if the relevance of items are so close to ranking that switches to items should not make difference. So I want to say defined, and other R's are defined. Okay. Then I define R aggregate. Then I define R aggregate, and how can I update BT plus 1 is the question. Then I need to go back and look at the click behavior, right? Shows me we assume B with BT, we define R aggregate T. We have R aggregate T, we have Rn of I. How can we define BT plus 1? Max is 1. For user N, item I clicked times our aggregate I should be 1. If item I is clicked. Item I is not clicked at all, what about that? Compute our aggregates. Okay, so this is complicated, and because I want to have a story, I use eta 1, eta 2. Because just saying something is the maximum and not defining the other ones, like what we learned, how smaller are the other ones, is not helpful, to be honest. And we can also, now I am more curious about Munzer's question. That he said, what is the perfect data set for having B pi I Ri? That's my story. That's how I wanna deal with it. But Mozart's question is also very legit. Ha ha ha. So we have eta t. Now we can define the R aggregate. That is true. Now this discrepancy between eta 1 and eta 2 solves a lot of problem. And so let me clear some of these bullshits I wrote here. Maybe we can ask ChatGPT to. Some of the time those are clicked, some of them are not clicked, and we have R aggregate. We can compute beta t, eta 1 or eta 2 over R aggregate t and do the average. Then over our aggregate t, exactly. And it gives us a new set of b's. Based on new set of b's, we can define new set of rn's and you come to new rn. Sounds good. That's a good story. And probably they say, oh, this part doesn't make sense or this part makes sense. And we have something to start with. That's what I care about. Better than having nothing, you know. Remember that talk from OpenAI that said at the beginning you can make assumption, then you can remove those assumptions. So this discrepancy was necessary. Okay, then we'll get to mechanism design part. Just one question from O1. Maybe we already know how to separate the effect of based on consumers' click behavior on a rank list. How can we separate the effect of the item's relevance from the ranking boost? Are machine learning models train models that include positions as a feature but are designed to predict clicks based on relevance, lambda mart, and neural rank. Eye tracking studies. That's good. Maybe we get back to the lambda mart thing because I like machine learning. Based on our aggregate T of I, we define the new B T plus 1 of my if item I for user n if item I is clicked en, or I can en eta 1 over our Um, right, TFI. If item was observed but not clicked, we define it as just edit it. Just edit 2, then define where was it? Okay, we defined this algorithm, but how can we say the algorithm should, what is the stopping time, right? Stopping criteria. We can say once the difference becomes so small, that is it. That's an algorithm. So we did this. Shit. Oh, max. Max on I, for example. Um, uh, I minus plus. Who knows this algorithm is convergent or not? I don't know. Right, let's go find this one now. An item's intrinsic relevance from the ranking boost due to position bias in click behavior is a well-known challenge. Well, so everybody knows it. Okay, everybody already people have done work on it. In information retrieval and recommender systems, when users interact with a ranked list, items appearing higher are more likely to be clicked, not necessarily because they are more relevant, but because of their prominent position. To disentangle these effects, you can employ several strategies. Click modeling. Position-based model assume that the probability of a user clicking on an item is the product of two factors, the item's relevance and the position-based examination probability. Mathematically, probability of being clicked given the position and the item is that probability of being examined given the position doesn't depend on the item. We can remove the item times probability of relevance given the item. Relevance doesn't depend on, so it is actually the same as Ri, B of pi I. B only depends on pi I, R only depends on I. User behavior model. Utilize models like cascade model or dynamic Bayesian networks to simulate user scanning behavior, capturing how user may skip over irrelevant items even in higher. Oh, we have this stuff. May skip over irrelevant items even in higher positions. Counterfactual learning and debiasing techniques. Inverse propensity score. Assign weights to each click inversely proportional to the probability of an item appearing at that position. What does that mean? Assign weights to each click. So we have a user behavior. They have a click. That user behavior has a weight, and we want to assign some weight to it. Inversely proportional to the probability of the item appearing at that position. I don't get this. This approach corrects for the overrepresentation of high ranked items. That's good. Weighted click is click. Well, we don't know the probability of position given the item. What? Wait, probability of position given the item? What does that mean? Doubly robust estimator. Combine IPS, advanced probability score, with a predictive model to reduce variance and improve estimation accuracy. Randomization, randomized ranking. That's we cannot do. I want to assume we have an offline ranking. Occasionally shuffle the rank list to collect unbiased click data across all positions. This helps estimate positions bias by observing how items perform when placed in different positions. Interleaving methods. Merge two ranking algorithms outputs and presents them to users in an interleaved manner. Analyzes click to infer which algorithm and thus which items perform better independent of position. A/B testing. Well, yes, but I am assuming we have an offline data. Conduct control experiments, and we cannot conduct experiments where you systematically vary the ranking of items by comparing user interaction across different ranking strategies. You can isolate the effect of item relevance. Statistical modeling, regression analysis. I like to know about this one actually. Regression analysis. Model the click-through rate as a function of both items, features, relevance indicators, and position. Uses statistical techniques to estimate the coefficient associated with each factor. Machine learning model. Train models that include position as a feature but are designed to predict based on relevance. Techniques like lambda mart or neural ranker can be adapted to account for position bias. Eye tracking studies. You may not be able to do this one. Use eye tracking to measure actual user attention on different parts of the rank list, providing direct estimates of position bias separate from click data. Well, actually asking ChatGPT is really helpful. Implementation steps. estimate position bias, use randomized data or click models to estimate their examination probability for each position, adjust click data. So wait a second, by the way, why do we want that? Because once we are done with homogeneous data, we want to talk about items that are completely different and come up with a DCG or a user behavior model for them. Adjust click data, apply debiasing techniques like IPS that click data to account for position bias, model relevance, validate models. Your model accurately captures them. By combining these methods, you can effectively see relevance from the artificial boost it receives due to the position in the rank list, leading to more accurate modeling of user preference and better ranking algorithm. By modeling, what I liked about Nagin's model was that they had this two-stage thing, where at the second stage, your ranking doesn't matter. At first stage, ranking matters only because of eyeballing cost. So it doesn't say that, oh, your position is so good times your relevance makes me consider you, but it says, oh, we have a consumer behavior that we know consumer cannot go very deep into the list because eyeballing cost increases. That was very beautiful. And also, once they are going through the list, they receive a signal about how good a product is. Okay, which one we should take further? So one thing I want to know is that, what is this one? So okay, based on studies, what is The user examines an item at a specific position in a ranked list knows as there is a key factor in understanding. Numerous studies have investigated how this probability varies with position, consistently finding that it decreases as the position number increases. That is, items ranked higher are more likely to be examined. Um, Why? I wish I had this in my thesis. Empirical models of examination probability. Exponential decay model. Many studies suggest that the examination probability follows as an exponential decay with respect to position. So expected utility will be, alright. And they're independent. That sounds stupid. Gem model where the examination is inversely well, I need the joint distribution. Alpha positive constant reflect. The probability decreases while exact values vary across studies and platforms. Trend is observed. Examination probability close to position 100%, position 2 85 to 90%, 75 to 80%. Gradual decrease to about 20 to 50%, 4 to 10. Drops often below 10%. Notable studies and findings. Interface design, user behavior, individual differences. So there are studies that have done this so far. We don't need to do that. Use randomized ranking. I don't like them. Perfect. It gives us the. So tell me how lambda mark works. Perfect. How lambda marked Okay, so it's also has the NDCG stuff. Is a machine learning algorithm designed for ranking tasks, particularly in information retrieval systems. By the way, expected utility of a consumer, if we have this fucking probability, is relevance, probability, click given position. Relevance given the item, which I call it R of I, and P of PI. And once they click what they get, the R of I, they get R of I. Oh, one other thing is that, what is the joint? Let me write this down too. Is it independent? For what is the joint distribution, meaning probability of examining position I and J yeah. So if we assume the exponential one, if we are observing rank 1 and we are assuming rank 2, the probability of observing rank 1 and 2 together is, it should be rank 1 times rank 2 given rank. Okay. So I'm now less worried on this stupid RIP of pi I thing. That's a stupid joint problem. No, that's very dumb. Scan sequentially. Yeah, exactly. It's just ignoring the. Stop, open, click. This is actually what we had in mind. No skipping, users don't skip positions. Exactly. Position I. User browsing model. Okay, they are more complicated these days. So all of these models have assumption, which is really good. What is it for the exponential model? I think we can interpret have all of those models for the exponential. Oh, that's just user chooses one of them. They don't observe two. Oh, okay. So their user model is that user chooses this position, just goes to that position and looks at, does not scroll down. Yeah, sequential model. I want a sequential model. No, I don't want this. Implies a position one. Examined, exactly. J, the joint probability is position J. Yeah, that means yeah, but is it congruent? This can be. Okay. No. Well, that was easy. Okay. Question I should ask is, mhm, do Nagin's paper was kind of a independent user search model. Wow, it's very interesting. We have this very small rainbow in the sky, and it's actually gone. Where is the sun? It's just very this size. Okay, that was. So these are all good. They are all good. We can have we have a lot of results. We have a lot of work done. We don't need to go very crazy. And actually, I like to keep these results. Just let's go over the lambda mark.
Introduction to LambdaMart. LambdaMart is a machine learning algorithm designed for ranking tasks, particularly in information retrieval systems like search engines and recommendation platforms. It combines two powerful techniques. Gradient-boosted decision trees, MART, an ensemble method that builds multiple decision trees sequentially, where each tree aims to correct the errors of the previous ones. Lambda rank, a method that transforms ranking metrics into gradient-based optimization problems by computing lambdas, which are gradients that guide the learning process towards better rankings. By integrating these approaches, Lambda MART effectively optimizes ranking-specific evaluation metrics such as NDCG, normalized discounted cumulative gain, and MAP, mean average precision. How Lambda MART works. 1. Learning to rank framework. Lambda MART operates within the learning to rank framework, where the goal is to learn a function that orders items, example documents, products, in a way that maximizes a certain ranking metric based on user relevance. 2 key components. Training data consists of queries, items associated with each query, and relevance judgments indicating how relevant each item is to its query. Objective: optimize a ranking metric directly rather than minimizing a traditional loss function like mean squared error.
Training data consists of queries, items associated with each query, alright, and relevance judgment, RIs, indicating how relevant each item is. Okay. Objective, so we have RIs. Objective: optimize a ranking metric directly rather than minimizing a traditional loss function like mean square error. Optimize a ranking metric directly rather than minimizing a traditional loss function. Okay, like ranking metric like NDCG, right? The role of the lambdas. Lambda calculations. Lambdas represent the gradient of the loss function. Lambda calculations. Lambdas represent the gradient of the loss function concerning the model's score for items. What is the loss function? They are calculated for pairs of items where the relative order needs adjusted to improve the ranking metric. That's nice. Gradient approximation. So we have a loss function, we know the gradient by the lambdas. Gradient approximation. By computing lambdas, lambda MART approximates the gradient of the ranking metric, allowing the use of gradient boosting method. Gradient boosted decision trees. MART. Gradient boosted decision trees. Ensemble learning builds an ensemble of decision trees where each tree is trained on the residual errors of the previous ensemble. I don't know about this part. Boosting process. Initialization. Start with initial prediction, all zeros. Iterative training. In each iteration, compute lambdas, fit a regression tree to these lambdas, and update the prediction. Optimization process. Compute lambdas for each query queue and for all pairs of items. Okay, for each query queue and for all item ij, where item I is more relevant than the item j. So we are assuming our i's. Lambda ij is minus loss si. What is si and sj? The score. They are the predicted one. Alright. Jesus. The lambdas encourage the model to increase SI and decrease SJ. Increase SI. Well, if lambda is negative. Lambda, okay, item I is more relevant. So one of them increases, one of them decreases. Alright, makes sense. Well, which one, I don't know. Fit regression trees. If we assume lambdas are positive, loss will be decreasing once we improve SI. Makes sense, okay. Fit regression trees. I need to keep these texts, these chats, for myself somewhere. I don't want to ask these questions from O1 all the time. Fit regression. Use the lambdas as target to train a regression tree. The features are the items, attributes, context, metadata, update, predict. Adjust the items scored by adding the scaled out tree. New SI of old plus eta f of xi. What is eta? Learning rate f of xi is the tree prediction for item I. Okay, I don't know what f is, trees actually. Repeat the process for a set of number of iteration or until convergence. Advantages of a lambda mart. Direct optimization of ranking metrics. Handling complex feature interactions. Decision trees capture non-linear relationships and interactions between features without the need for explicit feature engineering. Scalability can handle large data sets efficiently, especially with parallel computing techniques. Okay, detailed examples. My problem is that so far, honestly, this cloud is amazing. It's a cloud that turned into a edge of a cloud turned into a rainbow. Can I? So let me see. Where is it? Ah, here it is. Here, right here. So can you see it? I don't know. It should be here. This tree. Here. It should be here. I cannot see it in the camera. Oh, maybe I do this. Maybe now you can see it here. Here. This triangle. Only this one looks like a rainbow. The rest, nothing. So, yeah. Yeah, I think now it's better. Here. So kill the light as well before this kills us. Okay. So we are assuming we have the relevance score. For each query, consider all pair of items I and j where relevance of I is greater than relevance of j. Compute. Okay. What I wanted was computing Ri and computing B. Compute the change in NDCG of if item I and j were swapped. Well, again, it is assuming B of being of form 1 over log 2. This is the lambdas. Sigma is the scaling factor, training the tree. Target variable, train a regression tree to predict lambdas from the item features. Updating the scores. So what is the score? Score is the relevance. Impact of each tree, repeat the process. Hyperparameter tuning. Tree depth. Practical. Intensive. Sparsity handling. Extension and variance. XGBoost. Alright, if I assume users choose the product with the largest yeah, is the relevance of the item and B is the boosting effect. How can I learn these two functions based on what? User click model. User click data, not model. change this rename. Are you still working on this shit?
If I assume users,
You didn't give me any fucking answer, dumb fuck. Oh, wait a second, where is this probabilistic model coming? We said we maximize, user clicks on the product with the maximum this. This is a big assumption, motherfucker. Um, so again, in a similar way, they are using iterative estimate B by N, alright? Which is like 1 over log E step. Even initialize Ri. Mm-hmm. Okay, this is more interesting. Below a threshold, that's good, we have. So okay, this is quite similar to what I suggested. One other question I have is what is a decision tree? I know it's like yes, no, and then categorizes, right?
Introduction to decision trees. A decision tree is a type of machine learning algorithm used for both classification and regression tasks.
How is that
It
regression?
models decisions and their possible consequences in a tree-like structure of nodes and branches. Each internal node represents a test on an attribute, feature, each branch the outcome of the test, and each leaf node represents a class label, for classification, or a continuous value, for regression. Decision trees are intuitive and easy to interpret, making them popular for a variety of applications such as data exploration, predictive modeling, and feature selection. Structure of a decision tree. A decision tree is composed of root node, the topmost node representing the entire dataset or population. Internal nodes, nodes that represent tests on features leading to further splits. Branches, edges, connections between nodes that represent the outcome of a test. Leaf nodes, terminal nodes, nodes that provide the final classification or prediction. How decision trees work. 1. Splitting criteria. At each internal node, the decision tree algorithm decides which feature to split on and what threshold to use, for numerical features, or which categories to separate, for categorical features. The goal is to partition the data in a way that maximizes the separation of classes, in classification, or minimizes prediction error, in regression. Common splitting criteria include Gini impurity, measures the likelihood of an incorrect classification of a new instance if it was randomly labeled according to the distribution of labels in the subset. Gini impurity equals 1 sigma I equals 1 NPI 2 backslash text Gini impurity equals 1 backslash sum underscore I equals 1 caret NP underscore I caret 2 Gini impurity equals 1 I equals 1 sigma NPI 2. Where pip underscore IP is the probability of an instance belonging to class 3. Entropy, information gain, measures the disorder or impurity in the data set. Entropy equals sigma I equals 1 n pi log 2 pi backslash text entropy equals dash backslash sum underscore I equals 1 caret np underscore I backslash log underscore 2 p underscore entropy equals I equals 1 sigma n pi log 2 pi. Reduction in variance, used for regression trees to minimize the variance within each node. 2. Recursive partitioning. The decision tree algorithm recursively partitions the data. Select the best feature to split on, choose the feature that results in the greatest improvement according to the splitting criterion. Split the data, divide the dataset into subsets based on the selected feature. Repeat, apply the same process to each subset until a stopping condition is met. 3. Stopping conditions. Maximum depth, limits how deep the tree can grow. Minimum samples per node.
Alright, okay. Now, Oh, okay. We're just assuming. Logistic function. That's true. I wanna assume these two. Fuck that. Fuck you. Mm-hmm. Well, it's similar to expectation. The good thing is that this is not the something I can pick whatever because this is not what we are studying. What we wanna study is uh, whole set ranking. We need to know that to come up with a better idea for the whole set ranking where we have diverse list of products. Mm-hmm. That's nice. Crazy. For sure, we wanna keep this chat. Thank you, guys.